we're getting deep into the weeds of light, and I'm going to polish up some details about that. But let's see if we can't. Let's try to figure out what you guys do understand, and then I will try to patch in the pieces that you don't.
We were mostly talking about the wave like functions of light, and also about we talked about light being the communication between two atoms and
Good, good.
instead of and also electrons are a state of motion on the
Nice.
surface of an atom instead of being like an actual orb.
Yeah, I'm gonna so what I'm trying to build out for you guys is a way to visualize what atoms are doing to each other during light. Really during all of this mysterious phenomenon. And if you stick with me through next semester, it's going to be super important, obviously. Uh, my assessment since day one in this class I've been trying to share with you guys is that in some sense, physics has gotten increasingly obsessed with mathematics and these abstraction layers where they've kind of departed. A lot of fundamental concepts have been left behind in the dust because we have such powerful mathematics that allows us to build incredible technology. And that's wonderful for starters, but it has orphaned some really basic questions in the sort of dustbin of history. And so what I'm trying to do is provide some visual material basis for some of these invisible phenomenon based on everything we know about atoms and electrons and all of that. Now, that's not to say that the picture I'm painting for you is in any way absolutely true, but I do think that it gives us something to sink our teeth into that is congruent with all of the mathematics. So the picture that I'm painting for you illustrates all of this mathematics, but we don't really know because we can't actually zoom down to the size of an atom and look at it. So, okay, so we're talking about waves. We're talking about light is some sort of a waving thing, whatever that is, and it is an interaction between atoms. That's probably evidence. Hello. What else? Can anybody add to that picture? I'm gonna add the details that y'all miss. What else do we got? Lights. Yeah.
I mean, we talked like pretty briefly about like how we observe like our general understanding of it, like how a photon being emitted from an electron changing orbitals.
Nice, nice. Yeah, so the general schematic picture, the quantitative picture that often gets represented by this thing called the Bohr model of the atom, which is kind of that little plus thing with the little electrons going outside of it. We generally can think of light as having changed some sort of, the electron changes some energy state, whatever that means, and then it relaxes and we get a photon out of it. There's some sort of transaction that happens in it. And a photon is emitted, so we'll have to figure out what this photon thing means as we move along. But yeah, you're right. There's something happening to the electron. It's changing states. Electron, that's another bizarre word. What do you guys generally think of electrons as? Yeah.
I just think it is like the negatively charged particle.
Yeah, that's fair because that's generally how it's taught. The negatively charged particle part of the atom. What the heck is negative charge though? Right? It's very difficult to think about negative charge as anything other than the opposite of positive charge. And then you ask what is charge, and it's like it's a fundamental quality of the thing, right? So it's a bit circular and missing some pieces. So what I kind of tried to paint for you guys for a picture of yesterday was that what we know really about the atom is that when it gets more charged up, when it gets when the electron, which I'm calling the outer surface of the atom, some state of motion of the outer surface of the atom, when it moves into a new level, it takes on a new pattern of motion. The surface, whatever the surface material of the atom is, which we don't really have a word for, it takes on new patterns, right? So I showed you guys the Chladni plate as an example of harmonic structures that appear when you change the input drive to a system. Now this is an analogy, right? Because this is in 2 dimensions, first of all, and the outer surface of the atom is a sphere, essentially. So the harmonic structures that appear on the outer surface of the atom are going to be spherical harmonics, which is a legit discipline. We can model those, and I showed you some pictures of them last time, the way that people modeled these, right? So I think the real question, the piece of the puzzle we didn't totally build out yet is, what kind of vibration is the atom doing on its shell when it transitions, when it gets more excited, when it charges up? What is that vibration exactly? It's not this 2D, sand bouncing up and down vibration that we have on the Chladni plate. It's something a little bit more subtle. And so we need to build out a picture of that before we can understand how it is that two atoms separated by some distance can change each other's surface motion, i.e., change the polarity of each other, to change the charge states of each other, which is ultimately what light is doing, right? Okay. So I'm going to try to build that picture out a little bit for you. So if we actually have pretty cool microscopes today, if you want to call them that. I actually worked with these when I was working on my PhD, but they're basically these little tiny, tiny little diving board type things, nanoscopic diving boards that you vibrate across the surface of a material, and you shine a laser off the back of the diving board, a little cantilever, and therefore, you can amplify huge features from the surface because as the thing taps across the surface, it feels terrain. And you can actually image individual atoms using this thing. It's called an atomic force microscope. Now, the funny thing is, despite all of those surface features that I'm trying to point at, this is basically the best image we can get of individual atoms. They're little spheres, basically, right? So, this texture, this overdriven feature that we model mathematically. By the way, those structures, those little Chladni plate features that we get from the atom, so these sorts of things, right? This is what they actually end up looking. These are sort of different ways to visualize them for atoms, for the electron shell of the atom, right? This is the spherical mode of them. These are all derivatives of a mathematical model called a wave function for the electron, which is the best known way that we have of representing the behavior of this surface of the atom. It's called the Schrodinger equation for the electron, which is, the details of that are a little bit beyond us, but we have already talked about it in some sense, because at some point I pointed out to you guys that the wave function for the electron tells us that, yeah, it has this shell boundary, right? That your cantilever is touching some surface, but the wave function for the electron tells us that it extends almost indefinitely to some extent. So the surface isn't exactly something that just ends, right? I told you I tend to think of it as kind of this hairy structure. So this picture that we have is woefully inadequate for what atoms actually are, and trying to understand light or electricity or magnetism using this model is painfully inadequate. I hope I've impressed that upon you. So we end up with something that's a little bit better, which is we move to this kind of shell-like model. These are the distributions, so how much electron you're expecting to find essentially at any distance from the nucleus over here as it moves on out. And each one of these excited states is given a name. In this case, there's several, the 1s, the 2s, the 3s. We also have other names for them. You got a question?
Yeah, and I don't know why it's this specific visualization and the way you're talking about it that's triggering this thought, but is it inaccurate to call an atom with its electrons and protons some sort of like a capacitor or a battery in which the universe is storing energy? Like, because you have to have a certain amount of mass in the nucleus.
I think that's not an unreasonable. So the question is like, do atoms act capacitively? So you have to, people might not understand what a capacitor is, but capacitor is kind of like a battery or a flash bulb, right? It's basically you charge up two surfaces and you can discharge it. You can think of it like, I don't know. The answer is sort of yes. So in some sense, we could get into the weeds about what exactly an atom is, and that's kind of what we're doing. And maybe this question will make more sense at the end, but in some sense, yes, the atom tends to be some sort of stable vibrating entity, right? And it seems to have stable connections to its surroundings, right? I like to model these as sort of these hairs. I actually call them electron filaments, but I imagine that it has some stable connection to its surrounding. It's being driven, pushed, and pulled by its surrounding, by all the other atoms in its region. But yeah, in some sense, it is a stable, vibrating system, which I could see that as being treated capacitively. The capacitor analogy is a little tricky because a capacitor is an electric uh, engineering device, and
Sure.
we were working on trying to describe what electricity could be thought of.
I guess just like storing energy, because in order to create bonds between the atoms and stuff, you have to put energy into the system usually, right? And when we extract energy from it, those bonds are breaking.
Yeah, yes. I mean, everything kind of flows downhill. So once you understand what your the thing you're trying to manipulate wants, then you can just give it that. I think that's how a lot of chemistry works. You know, you're like, oh well, it prefers to be bound with this guy versus this guy, so I'll use a catalyst to break it apart. And yeah, I think the bioengineering, or the not bio, but just chemical engineering side of manipulating atoms is a lot about understanding what they would prefer to, who they'd like to be hanging out with.
It's just a curious thought. I don't know why that.
That's all good. I love it. Yeah, it's a good. And let's come back to it as we go, because I'm going to go a little bit deep here, and you guys might be like, "Geez, this is an astronomy class. Let's talk about planets and stars." We will get there, but I really, really think that it's important that we don't just think about light as these magic bowling balls that are being shot off into the world. And so I'm gonna ask you to bear through this as we try to picture what light is, what the atoms are actually doing, because I think downstream of this, we're going to be asking a lot of questions about the signals that we're getting and what they mean, especially with the outer planets. Um, and we have to understand light in order to make sense of that. And honestly, gravity, orbits, all this stuff, it depends on a really rational model of the atom. So there's a couple of other things. I pointed out earlier when I was talking about gravity that, gravity actually makes a lot of sense if you consider that the outer shell of the atom isn't just a shell. It's actually got some sort of thinned portion of it, which is capable of contacting its neighbors. Also, the fact that both light and gravity sort of fall off with this very radial model, right? So the intensity of gravity, the intensity of light falls off with an inverse square, which isn't important. The mathematics of that aren't super important. But the basic principle is that there's some sort of radial presence of the surface of the atom. I think that's a reasonable way to visualize what's happening, is that the presence of the atom seems to fall off in a radial manner. Again, I think about this as, visualize this as sort of hairs from the surface of the atom. I think that's a reasonable way to think about it. So, where does this leave us? The last piece of the puzzle really comes down to, okay, so we have a way of the atoms in a light transaction of interacting with each other, but we still don't totally understand what the heck this vibration is at its surface. We don't totally understand what it means for an electron to be charged into one vibratory state versus another. We know it changes the shape of the surface motion pattern, this Chladni plate kind of stuff. It changes all of that. We get different orbitals. What the heck does that mean? All right, so we have to think about this a little bit deeper. One of the things that we know, and this is kind of a rough illustration of the way that I'm thinking about illustrating a very simple atom with one electron, simple 1s shell. It's sort of got radial projections. It can interact with its neighbors these ways and apply the same pressures at its surface to its neighbors. One thing that we know about the electron, about this particular vibration that it does, is that, and this is super deep, but I think that this is way more technical than we should probably be going, but I think it's really interesting. There's this strange quality that electrons have, which is called spin. And spin, electron spin, is a strange quality because it's supposed to describe the angular momentum of the electron. So angular momentum is what? We've talked about this back when we were talking about Kepler, I think. Does anybody remember angular momentum, what this means?
I remember it, but I don't remember how the words to describe it.
Okay, it's okay. It's nothing crazy. It really just kind of, it's sort of a vector that describes the way that something orbits a center. Let's put it that way. Now,
I know about the analogy of like a dancer putting their arms out.
yeah, that's a great analogy. The figure skater is one I hear a lot. So angular momentum is one of those conserved quantities that Newton, Kepler were concerned with. In some sense, it helps us quantify why orbits remain stable in the way that they do, and why the inner planets go faster than the outer planets. So you guys ever seen the figure skater? They're like doing this little triple axel crazy, I don't know what the heck figure skaters do, but then the figure skater is spinning at some rate, and they bring their arms in, and they start spinning a lot faster. I'm not going to do that because I'll get dizzy and fall over. But there's something that happens when you bring your center of mass in tighter that keeps you moving. And the answer to that is angular momentum. It's the quantity of spin motion that you have, right? So if your pieces of your body, your arms and legs, are further away from you, they have to travel more distance as they spin around the center. So if they're here, that same amount of motion has to be conserved, right? I have to keep moving the same amount, and the only way I can do that is to spin faster because these pieces don't have to move as far anymore, right? Okay, so angular momentum. Now, the weird thing about the electron's angular momentum is that the quantum mechanicists have kind of given up on it. It doesn't make a lot of sense to them. And the reason it doesn't make a lot of sense is that it has a strange kind of symmetry to it, which is uncommon in our everyday life. As this symmetry, which is referred to as spin 1/2. Now, the symmetry of the angular momentum quality of the electron is so bizarre because, unlike a globe or something, what happens if I take a point on something circular? Let's assume this was a sphere. If I rotate it 360 degrees, I get back to my starting point, right? Make sense?
Mhm.
The weird thing about electron spin is that you actually have to rotate a point 720 degrees to get back to your starting point, which is really, really weird. And so it's generally described as not a true quality that can be imagined or rationalized because, generally speaking, the electron is thought of as this magical bowling ball that orbits the center of the nucleus. However, there is a solution to visualize spin 1/2 that is much, much more sane. I don't know if it's true or not, but I think this will help you understand it, at least visualize what's going on. And the way that I do that is I actually imagine that instead of the outer surface of the atom rotating like a globe, it actually curls back in through its center in the shape of sort of a donut, something like that. I've tried to illustrate that here for you guys, and I did it by putting a pink line on this thing. And there's a little rip in the side of the atom that I've drawn here too. Because you can see that basically what happens is the atom has to spin twice before its surface has rotated through its center back around to its surface. So this is how I illustrate this spin 1/2 business. Now, this isn't just arbitrary that I'm telling you this. I'm telling you this because I want to give you a sense for how in the world atoms can transmit this electron motion to one another. So if you go and study light, and we've been talking a bit about light, it is some sort of wave of electromagnetism that's being transmitted between atoms. One of the ways that this guy does great work, 3 blue, 1 brown, but what he's shown here is essentially if you were to take some sort of device and measure the electric or magnetic field at any point, what you would see is you would see that some sort of oscillating presence. The direction of charge, plus versus minus, keeps changing at every point. And so, anytime you stick your device in there to measure it, this is sort of the predicted outcome, which is nice, and it's pretty much as close as most people get to visualizing light. But what does this actually mean? It means that the atom itself is first of all changing its charge, and without a sensible idea of what charge means, you don't have any idea what's actually being transmitted at the end of the day. So I think a better way to visualize this is something like this. The atoms, this is if you can imagine a single atom wire, okay? This is like a switch that I'm going to close between these two wires. The negative atom has more surface motion than the positive atom. The motion is defined by that spin 1/2 motion, which is the sort of rotating and involuting motion. What happens when you take one that has excess spin motion and you connect it to one that has deficit spin motion is you transmit the motion from one column of atoms to the other. So you can imagine you have a wire, you stick them together. What you've done is you've made a sink for that spin motion from one column to the next. Questions? Again, I'm not saying this is true. I'm saying this reflects the mathematics perfectly. And it's a lot more sane than just some sort of, plus and minus things that have no physical meaning whatsoever. So this is a really good way that I like to visualize it. Now, the result of that, if you include this kind of hairy outer shell of the atom, The result of it is that when you alternate the direction of the transfer of that motion, you get this column that's basically flapping back and forth like this. And its extended structures are going to convey that exact same motion. So you can imagine, first of all, it's gonna, as the things go back and forth, the atom has a real surface to it. Its extensions are made out of some sort of real material. And what do we know about real materials? When they're, if I was to take a rope or something and whip it back and forth, sort of, this is just a quick Blender mock-up that I did. Oops, where'd it go? Oh, I guess it disappeared. We'll stick with this. If I was to take a rope and whip it back and forth, what would happen? It would transmit some waves down it, right?
Yeah.
And how long would it take for the waves, let's say you were at the other end and I was doing this, how long would it take for the waves to get to you?
Because of the energy at the input of the system, right?
It actually depends almost exclusively on the material properties of the rope.
Oh, yeah.
So if the rope is really, really, really stiff, it'll be really fast. And so this is interesting because light has a defined speed. Nobody knows why the speed of light is the speed that it is. It is really, really fast. So in our analogy, as this column is whipping back and forth and these waves of light are going out, right, as the thing's being depolarized and repolarized, these waves of deformation in these extended structures are really, really fast, actually. They're really, really fast. There's something like 300,000 kilometers per second, something insane. Just like impossible to imagine fast. So whatever the heck the atom is made out of and whatever its extended structures are, they're probably under great tension so that they have extraordinary stiffness. They might have extraordinary stiffness on their own, but this isn't completely unreasonable. So, something like spider silk is a cool example, right? Spider silk is incredibly tensile, has incredible tensile strength, actually. It's on the order of steel, actually. Now, the thing is, it's so thin that you can break it with your hand, right? But if you were to scale it up to the size of a steel cable, right? So I think we're facing something like that with whatever architecture these networks of atoms have too, where there's some extraordinarily tension structures that are allowing the atoms to interact with one another. Therefore, the waves of deformation in those structures are extraordinarily fast as well. Which makes sense. They're probably incredibly thin, they're probably incredibly rarefied, especially at a distance, and they're probably stretched really tight because holding bodies to one another puts a lot of tension onto a system. So then we can kind of like roll back to our picture of our basic idea about light, which comes from the antenna. So, again, I think the antenna is the best laboratory for understanding light because we can see what the atoms are doing at one end and we can see what they're doing at the other end. And again, the reality is that the polarity of the atoms in the column is changing from plus to minus to plus over and over again. And the frequency at which it changes in concert with the dimensions of the length by which the wave needs to travel gives you the wavelength of light that's going to be outputted from your antenna or received from your antenna if you're tuning it to receive a signal. So this is the most rational picture I can give you of light. The atoms have some sort of surface. They have a real surface, I believe. I think that even if you don't want to believe that, it's easier to think about it that way. They have a real surface. The surface is in some sort of motion, which we call the electron. The electron has different states of energy, and as it's charged up, it goes into higher and higher states of energy. And those states really reflect the different patterns of that spin 1/2 motion. They're true rotatory and involuting motions that can be visualized that way. And the transmission of that motion from one atom to the next is electricity. The transmission of that motion at a distance has to do with the extended structure and the equatorial motion of those same structures. So this is how I want to be thinking about light. This is this sort of network means of thinking about light, not magic bullet balls, but true interactions between atoms who have surfaces which are extended and are actually capable of mediating interactions like this. Again, are the atoms in my eyes directly connected to yours when I'm looking at you? I don't think so, because there's a lot of atoms in between us. So there's some sort of incredible relay systems that are going on in nature. I think that this is all a very complex game of relay. And so we were talking before about diffraction, right? Or was it diffraction? Yeah, and interference and so forth, right? Darkness and shadows. The ability to project shadows onto a screen into the light part of the screen. Again, that was really a demonstration of network effects where you have out-of-phase signals. Some atom is getting told to be charged into a greater state of motion while it's also being drained of that same motion from a partner atom, and the phases are mismatched, and you actually get darkness as a result of it. Doesn't mean that there's no signals going on, it just means there's mismatched signals going on. All right, yes.
I'm curious if it's your intention when we're talking about light in this way, with your rope analogy, is the rope space-time effectively that is pulled to a tension and the waves that are passing through it, like, so that is what's controlling the speed of light.
I don't mind that you think that you would say that. I wouldn't say that. The only reason I wouldn't say that is I'm really allergic to taking a concept like space-time
Yeah.
and treating it like a physical material structure. I'm actually saying the atoms have a physical material structure,
Okay.
and that structure is extended in space. And so I'm saying that space-time is a concept that reflects predictable trajectories of material bodies. So the way that a body is going to behave near a larger body defines space-time. The way that light behaves in the presence of other bodies defines space-time.
In that same vein,
Space-time is kind of like the field, right? I showed you this field from 3 blue, 1 brown.
but if we throw out the concept of space-time, say, okay, space is actually just this net energy extending into infinity of these interconnected atoms of that existed. Like you don't have to have space-time, but like the medium could be the net energy that goes off to infinity, right?
Yeah, yeah.
This intention that light is moving. Right?
Yeah. I mean, it's so close of an analogy. In fact, there's this wonderful physicist I know at Princeton who's done this paper where he calculates the stiffness of space-time in like 6 different ways.
Wow.
And I'm reading the way that he calculates it, and I feel like what he calculates could easily be substituted for the tensile structure of the extensions from the shell of the atoms. And right, so he's calling it the stiffness of space-time. I'm like, no, that's actually the stiffness of the tensioned structures that emanate from the surface of the atom. I think we would come up with the same quantitative answers.
Oh.
So in some sense, like, I'm totally fine with saying this is, my main problem with both the ether theories of old, which we've talked about a little bit, and with space-time as pseudo-material, is that they're both isotropic and homogeneous. What do I mean by that? I just mean they're kind of this always the same goop, right? Whereas I'm saying, no, the structure, the goop has structure, and the structure actually defines why it is that a large body has this gravitational presence. I don't have to say, well, it just is. Like, it's massive, so it attracts things. That's kind of where the buck stops with space-time. So if you think about like Einstein, maybe you guys have seen this analogy where they have like a bowling ball on like a trampoline or something, and the little one rolls around it. But then you got to ask, like, why is the bowling ball doing that to the trampoline, right? I'm saying the reason the bowling ball does that to the trampoline, why it actually bends the trajectories of the littler things, is because it has radial architecture, which means that it's more connected when you're nearby to it, and it's more connected in an inverse square law because surface area gives you the proper connectivity as a result of it. That's why I keep showing this this picture over here. Where was it? That one, right? So just radial architecture gives you the proper inverse square law of connectivity to begin with for light and for gravity. Yeah.
Can you elaborate on what you mean by radial structure?
Yeah, so if you can imagine that these little rays that are coming out aren't just rays, but they're actual hairs. They're evenly spaced on the surface of a spherical body. The presence of those rays is gonna, or those hairs, is gonna fall off with an inverse square law. So your connectivity to your neighbors that is gonna fall off with an inverse square law.
Okay, so then how would a larger collection of them increase the length of those hairs?
It will increase the length, it will increase the connectivity. So as you go nearer a structure that has a lot of atoms, you'll be more connected to those atoms, and you will experience greater tension towards them and more pull towards them. That would be in proportion to the square of the radius of those
Because
atoms.
those hairs extend infinite. Okay.
Yeah.
And it's a finite number of points, right? Because otherwise you bump into like Barnard task.
Yeah, it's got to be finite, of course. I don't know how many or anything like that.
Right.
Yeah. It's again, this is this is a way I think of at least at the bare minimum of visualizing how a mechanical representation of these fields and force effects could be playing out. I have no way of knowing if this is true or not. We don't have the technological means of zooming ourselves down to the size of an atom and checking it out. But I've been working on visualizing this for many, many years, and I was very tired by the time I was about 30 years old of hearing that things just didn't make sense down at the level of the atom. It really started to bother me at some point. And so I think that all these things can be rationalized with a proper architecture for the atom that's capable of doing everything from light, gravity, electricity, magnetism, all of these otherwise magical things, which we have to basically just model as numbers or fields, where fields are really just the vector predictions of the effect that will be measured. They're not actual entities capable of doing anything. All right. So, what else? Questions? So, anybody? All right, because we're gonna go.
In the weeds.
Yeah, we're deep. This is about as deep as it gets.
Aren't we not going to get deeper when we're getting into photons?
Yeah, goodness gracious. Yeah, we do have to deal with photons eventually, but not as much as next semester where it starts to really matter because photons have been horribly misinterpreted. We will talk a little bit about them. I'm going to introduce some basics of telescopes. We'll talk about photons because we have to talk about spectroscopy a tiny bit, although it does play into some of our downstreams. And then, so let's do that today. And then starting next week, we will actually start investigating the planets. So anyways, I hope this was useful to you. I hope at least 2 or 3 of you, this will impact your lives positively. Drove me absolutely batshit crazy when I was a kid that the atom was just doing all this magical stuff and nobody could help me with it. And so
It does it because it does it, and that's as much as we need to know.
yeah, there's a lot of that. And so anyways, let's keep going. Let's go. All right. So, who here has a telescope? Anybody? Nice. Few of you?
I have that.
You've had one? I've got one. It hasn't gotten a lot of use this year. There's some basic pieces that I think are worth paying attention to, but the concept is pretty straightforward. At least this is a special kind of, this is kind of the classical original type of telescope. It's called a refracting telescope because it uses lenses to magnify. We kind of touched on this with Galileo earlier, that nobody had really thought of putting the lenses in a line. They had lenses, what did we decide, for quite a while.
Several hundred years.
Several hundred years people had lenses, and then one day somebody decided to put them in a straight line together, and voila, the telescope. So the most simple kind of telescope we can imagine is this refracting telescope. Let's see, what can we say about it? Doesn't really matter how it works since we're not going to be using them, but people almost immediately after Galileo started pointing them at the sky, coming up with all sorts of interesting things. This is one of my favorites. Actually, this is also one of my favorite scientists of all time. This is Christian Huygens. he was responsible in some sense for a lot of the really interesting early wave theory stuff, duking it out in some sense with Newton. I think they were a different generation, but they were very much opposed about how light worked. But Huygens put this huge lens up in a tree. That was how he made a huge telescope. The eyepiece was down below. And using this system, he was able to actually make the first drawing of Saturn. Have any of you guys with telescopes ever seen Saturn? Yeah, pretty cool, right?
Yeah.
You know, you can actually, if you guys, even if you don't have a telescope, do you have binoculars, anybody? Binoculars are cheap. If you get like a 40x binoculars and you put it on a tripod, you can see the rings of Saturn and you can see the moons of Jupiter, and it's a surprisingly profound experience, actually. There's something very different about seeing a picture of it on a screen versus seeing it in the sky with your eyes. It is really, really weird and awesome.
I'm kind of sad that I will most likely outlive how long we can see the rings
Oh,
because it's gonna go
they're dissipating? I don't know how fast they're going. Oh, yeah, that is true. That is true.
line, so that
How long are they going to be flat for? I don't know.
I didn't remember several hundred probably years.
Oh no, really?
That.
I have to look into that. I don't actually know. I do know they went flat recently, but I don't think it's going to be that long. But you're right. So Saturn has a tilt just like the Earth. We'll deal with Saturn in its full glory. But yeah, if it's tilted in such a way that it's tilted towards us, we get a nice view of the rings like Huygens drew here. If it's tilted on the side just perfectly, we can't see the rings at all. And that's a little depressing. So this method of using telescopes was cool for a while. There's a problem though with lenses. Chromatic aberration. Yeah, you know what this is, eh? A little bit.
So you use it a lot with cameras.
Yeah,
it's
exactly.
an effect that you tend to people add in like video games as well.
Huh.
Because in cinema, cameras have an amount of chromatic aberration on the edges, usually of people or subjects, where the light tends to refract.
Kind of spreads the colors out, right?
Yeah,
it's actually quite beautiful sometimes.
The RGB.
Yeah.
But
this can be quite pleasant.
yeah, usually it's done to give like it's done intentionally to give like a surreal
Like
effect.
a kind of romantic vibe or something.
Same reason that like lens flares are done intentionally.
Exactly.
Yeah.
So that's great if you're making movies. It's a nightmare if you're trying to look at something
super blurry
in the sky, right? So this is an interesting phenomenon, actually. You know, the way this is often taught in textbooks is that materials have, as light travels through materials, it slows down. This isn't quite right, though. That's not exactly how it works. Although the forefathers all thought that they could explain it away this way. In fact, they thought, well, materials are more dense, and so if they're more dense, then the little light particle thingies have a harder time and they slow down, which is like, it's a good try. It's not. So unfortunately, people realized that wasn't true because they had denser transparent materials through which light did not refract more. So the index of refraction has some correlation with densities, but very little actually. And so the result is that we have this thing called the index of refraction that tells us how much light is going to be bent by some medium. So there's a particular index of refraction for this prism that's drawn up here. And it's even worse because they call it optical density now. Although it has nothing to do with the mass density, like how much material is there or anything. And this makes for terrible confusion down the road. What's actually happening, if we go back to our kind of antenna model of light, and I stole this from 3 Blue, 1 Brown, this image and the next one, is that what's actually happening is, just like everything we've talked about, light is always, it can be thought of as an antenna transaction. There's always some atoms that are talking to other atoms. So what happens is that inside of these materials, like the prism, there's a lattice of antennas, basically. There's a crystal structure, and even if it's not perfectly regular like a crystal, it still has domains, you know, like water or something. It's still going to have transient structures. It has a transient lattice. So what happens is the light interacts with the first column of antennas. Now, the problem is that that column also has some of its own charged entities in it. So they're doing their own dance. And the incoming signal resonates the antenna, but it's also kind of pushed back on because it's got its own standing vibrations in it. These are the kind of vibrations I spent the first half of the class talking about. They're not displacement vibrations, they're electric vibrations of the shell. The result is that the wave essentially gets out of phase with itself. It's another example of destructive interference at the level of the antennas. And what happens is that the wave, if you think about the whole wave as a whole, it kind of gets truncated. And the result of that is that the front actually appears to move slower. But in reality, it's not moving slower. It's just the wave's getting squished because little pieces of it are getting chopped off. So, again, probably way more detail than you care to realize, but light doesn't really travel slower inside of media. It's just that there's a complex antenna phase interference that causes it to look like it's going slower. This is
Which makes sense since the speed of light is constant.
yeah, exactly. And why is the speed of light constant?
Can't possibly move slower, so
Why is the speed of light constant? I didn't probably beat this home enough when we went over it before. But with my jump rope analogy,
It's constant in a vacuum,
it's
right?
well, it's constant. I believe that it's constant. Period.
yeah.
It's just that
Theory of relativity relies on the simple fact that light is the speed of light is constant for all observers, regardless of where they are or the material the light is passing through.
yeah. So that's a good point. So the standard treatment that we have for the behavior of light in let's say cosmic situations is special relativity. I'm not making this assertion based on special relativity, although honestly I think what's his name, Grant Sanderton, who made these visualizations, was probably trying to rectify the constant speed of light with the slowing of light inside of media. I think that light has a constant speed for a very obvious reason, which is that any material has a constant speed of deformation in it. So if I slam my hand on this material and I measure the speed at the other end with a microphone or something, how long it takes to get there, it's going to be the same always in this kind of material. So assuming that the atomic shells and their extensions are made out of the same stuff everywhere, well, then I would absolutely expect them to deform at the same rate everywhere. There's no reason that should be different. Now, of course, there can be all sorts of weird phase interferences that might provide the illusion that the light is slowing down inside of a material, but this can easily be explained as phase interference of these different antennae fighting back against the impulse that they're being driven by.
So I worked a long time as an audio engineer
Nice.
in the publishing industry for audiobooks.
Huh.
And this image is giving me vibes of when we start talking about sample rates and the fidelity of a piece of audio.
Mm.
So my question is, when we're looking at this, when light is passing through this sort of refraction entity, is there a loss of fidelity of the light? Like, are we losing information when it's moving through this kind of medium?
I don't think we're actually. I thought you were going to say impedance matching, actually, because
Oh, no.
sometimes microphones like to be driven by a certain impedance, which is like a difference, which is closer to the idea. I don't think this is lossy because the reality is that as soon as if you see when it comes out of the other end, it's still emerging with perfect fidelity out the other side. There's no real information lost. It's just that the destructive interference that happens along the way appears to carve out little pieces of the wavefronts, right? It's a very if you're just measuring the speed by the motion of the wavefronts, it looks like it's slowing down. This is totally an illusion that it's slowing down, is I think the point that I'm trying to make here. Because the reality is that as soon as it stops being interfered with on the other side, as soon as there's not a lattice to fight back against it, you don't have any of that, and the light peaks appear to be traveling at the normal speed. Yeah.
Which
It's
my thought is just that makes sense because again, if light was like sound, for instance, right, or any other energy that gets transferred through a medium, um, if it gets slowed down in a certain medium,
it should stay slow.
it doesn't just revert once it's done.
Yeah. Yeah, that's a great point. That's a really good point. Yeah, it cannot be a true speed change.
Into the surrounding objects.
That's right.
Light doesn't do that, so therefore it can't actually be slowed down.
That is a really, really good point. So what Dante is saying is that in something like sound, which is longitudinal waves of collision, if it were to slow down, it would literally lose energy and it wouldn't be able to resume its former travel speed once it entered into a new medium. That wouldn't make any sense at all. So there's no way that light can actually slow down inside of a medium. It can only appear to slow down. And I think Grant's illustration of how this happens is just fantastic. He's got a few videos on YouTube if you want to check him out. I freaking love his channel. It's really, really
What's
good.
the channel called?
It's called 3 Blue, 1 Brown. He's just complete super boss, the highest level in my book of people who explain things in ways that make sense. Now, he's not as obsessed with material explanations as me, but he does get to the bottom of things like this, which are incongruent even with the standard theory like special relativity. 3 Blue, 1 Brown.
3 Blue, 1 Brown.
3 Blue, 1 Brown. Yep. Weird name, but
Is one spelled out or is it the number?
that's a great
You
question.
can look for it either way.
Yeah.
Yeah, I think
It's just the numbers for both.
You guys know him.
Okay.
Yeah.
Yes, I recommend his Essence of Calculus series a lot for people.
Yeah, his math stuff is great too. And if you guys ever get into higher level physics, he does such a good job of just visualizing complex principles, why we use complex numbers, what's up with the wave function, all that stuff. He really takes the sort of spookiness out of a lot of things.
Complex numbers.
Yeah, you could just binge this guy's channel. It's incredible. But I love this one because it kind of fits really nicely with my material conception of light. So anyways, this happens inside of lenses and it's a disaster because it makes things blurry, right? And so people messed around for a while with ways of working around this, right? So they actually would install other pieces of lenses that would bend the rays, concave lenses that would bend the rays back into place, right? So they would correct for this as much as they could. That can get you pretty far, but it's still not ideal because there's limits on the focal length and things like this. So enter the reflecting telescope. This is actually the kind of telescope I have. They're the cheap ones because guess what? Lenses are really expensive to make. You have to polish them and grind them. They're heavy. They're kind of a nightmare actually. But somebody realized that you could just take a mirror that was convex and take all this light and focus it back on a single point where your single little lens is. So you have a cheap little lens as opposed to this huge giant lens that you're trying to deal with. And you have a mirror at the back. So this is probably, if you guys just go out and get like a couple $100 telescope, this is probably the kind that you will come across. And they're fantastic. I love mine. It does require a little bit of messing with the mirror to get it to align and focus on that point exactly, but pretty cool. So, oh, by the way, I should have put this earlier, but this is a giant refracting telescope from Mount Wilson, I believe, in the early 20th century. They had these huge lenses. These things were like super heavy and difficult, and they were dealing with this chromatic aberration. Whereas on the other hand, nowadays people just use these giant mirrors, right? Now, the other advantage, by the way, once you get a giant mirror versus a giant lens is that they're a lot less heavy, right? Now, this might seem crazy, but glass is actually, it actually deforms under the weight of, under its own weight. So these huge lenses, the bigger you make a lens, it actually becomes a problem because it's so heavy, it starts deforming, which warps your image, right? You don't have that problem with mirrors because they don't weigh that much. So they're much less subject to that kind of weight deformation situation. So that's good. So a lot of telescopes these days are refracting telescopes. Reflecting telescopes. What else have been some cool advancements? This is the Mount Palomar mirror. I have some friends who live down there in San Diego. Very cool observatory you can visit. Now, people started doing these hexagonal arrays because even though mirrors weigh less than lenses, they still deform a little bit under gravity, right? And this can be a real problem. So if you chop the mirror up into little plates and you put little sensors on them, you can actually keep them aligned in such a way that you can put all these little pieces together. You can stitch them together in post-production, as it were. and get a more stable image. And as you can imagine, this kind of thing is really important if you're starting to send telescopes up into space, because you need lightweight stuff to put it on the back of a rocket and get it up into space, right?
Because hexagons are the best elements.
So the other cool thing about these hexagonal arrays is that they can put motors on the back of them, and they can actually adjust for things like atmospheric refraction, because just like lenses refract, so does the atmosphere, unfortunately. So most telescopes that you'll find, the big professional ones, are going to be where? Where do they put them? On mountaintops. Where else?
In space.
Space, obviously. What else? Deserts, right? Because it's dry. There's not water to do refracting, right? So dry desert mountains close to space are like your best bet. But even then, you still have to deal with some refraction from the atmosphere. And so, this was an image, an early image of Jupiter that was taken using this principle of adaptive optics. That's a hard one to say too. Where the actual lenses are correcting for the atmosphere as they image whatever you're trying to take a picture of. So that's kind of cool. What else do we want to say about this? Obviously in the modern age, detectors have gotten a lot better. So, we can actually use the little CCDs that you have in your phone, right? There's just arrays that actually can count the, number of waves that they're really getting smacked with of light, right? So you basically have the same thing introduced today, where there's these tiny little photo detectors that are being installed on these telescopes. It wasn't always the case. In fact, there's a huge, long story that I don't have time to get into. I actually love this book. If you guys are interested in the history of astronomy and all, there's a book called Glass Universe. I would tell you more stories from this book if we had time, but it's probably getting close to where we need to get onto the planets. Originally, when people first started doing this industrial level astronomy back in, let's say, the 20s and 30s, when they started building these huge telescopes like the Mount Wilson version that I showed you earlier, they literally had to. How would you know the brightness of a star, for instance, right? How would you do that? How could you say how bright a star was? Any ideas?
Probably by measuring how much light came in from it.
How would you do that though before CCDs? CMOS. It was pretty crazy. So what they'd do is they'd actually have two eyepieces, and one eyepiece would be focused on some standard, right, like Polaris. And they would say, Polaris has a brightness of 2, right?
So it's relative.
Yeah, it's relative. And then there would be somebody sitting there who would just they would basically turn a dial and to let more light in to the star that they're observing until it was the same brightness by eye, completely subjectively, with Polaris, let's say. I don't know if they used Polaris, but they had some standard reference. And that dial would basically tell them the multiplier, and they would get the standard of magnitude for the stars. This is all done by hand, yeah.
How would they be able to tell if there was like maybe debris in front of the sun or like some other object blocking it? Like, would they be able to tell the difference?
Well, that's a huge problem today, even, honestly. You guys, Betelgeuse in Orion's shoulder? You guys know this one? You guys know Orion? We talk about Orion? A little bit. It's probably one of the most recognizable clusters of stars at night. It's those 3 that are in a row if you go out at night. But up in the shoulder of Orion, so above the belt, it's the left-hand shoulder, there's a star that's big and yellow, and it's more big and more yellow on some days than others, which is pretty weird. And there's been an ongoing debate since I started teaching this class about what in the heck that is. Some people think it's dust. Some people think that it's, asteroid debris in the way. Some people think that the star is actually going through some sort of cycles, right? And
I've even heard the argument that the star is dead and we're seeing a supernova, like a nova, not a supernova.
yeah, it could be baby novas. Yeah, it's casting off layers of itself. I mean, That's a really interesting piece. And then there's, of course, so why do stars brighten and dim? That's like the real question. And what sorts of things could do that? I think there's some other possibilities too, but you guys are going to have to take next semester to get to the bottom of that because it's just too big of a discussion.
For something like that, what would they say for the luminosity of the star? Would they say it's like indeterminate?
They would just say that it's this on this day and this on that day. Yeah. Yeah. So that's kind of interesting. And some of these stories are told, and it's really crazy because a lot of this work was being done during the war years, right? World War I, World War II. So all the men were away at war. So a lot of this work was being done by women. Um, they called the women. So there was usually an astronomer in the room with this telescope who would be writing down the things. They wouldn't let the women do that because women get cold or something, and they didn't want them to be exposed to the night air. But all of the women were crunching all these numbers and coming up with these systems. So most of the systems we have for classifying stars, the spectral stuff, was all laid out by these women who were actually called computers at Harvard. That's where this stuff was done, which is really crazy. And that whole story is laid out in this book, which is just actually super fun to read. So yeah, I was telling you guys about the standardization of magnitude there. What else do we want to say? Okay, well, one nice thing that comes out of this refractive thing is that, you know, and if you're interested more in the like antenna explanation for why this happens, again, check out Grant's work on YouTube. But the effect of the apparent velocity of light slowing down means that different waves separate inside of a prism. Again, this is much more of a phase decoherence situation than an actual speed change. But that doesn't matter because at the end of the day, what it means is that different wavelengths of light separate spatially when they emerge from the other side of a prism. This is really useful because it means that you can start to fingerprint different objects in the sky, right? Now, this was all well and good, but people, surprisingly, when they discovered this, did not have a way of registering it. They could see the colors splitting, but they didn't know what to do. They tried to draw pictures. It's a very difficult thing to capture. And it turns out that there was this really strange couple who lived in upstate New York named the Drapers. I think the husband was a physician. His wife was just into photography, and they're both really into astronomy. And they figured out that you could actually photograph these spectra as they were splitting behind a mirror. And this whole story is inside that book too. But they're a really crazy couple. They're just so obsessed with building these telescopes. They actually went on their wedding night, instead of having a party afterwards, they went shopping for glass in downtown Manhattan that they could melt down and make lenses for their telescopes out of. So they're super obsessed. But they basically, this amateur couple, developed the idea that you could take the then pretty unrefined art of photography and match it to astronomy and actually photograph these spectra as a result of it, which is pretty cool. And the results is that people have standardized this to the nth degree at this point, and we can use these CCD devices and make really, really refined pictures of what colors of light are coming from any particular body in the sky at what degree. And the result of that is that we can learn a lot about those different bodies, right? So, I pointed this out to you guys last time, that the reason visible light, that we're so well adapted to it, is probably because it's the peak wavelength emission from our own star, right? So our star emits visible light more than any other light, right? Now, this is interesting because our star actually, this is a picture of the light from the surface of the sun called the photosphere. But and all the stars emit continuous spectrum of light. So all of these wavelengths are represented all the way out into the infrared and beyond, right? Far, far long reds. They also have some really small amounts of high energy, short wavelength photons, ultraviolets and even some gamma rays and X-rays, right? But very few. So every star is a little bit different. Its spectrum is shifted depending on its temperature. And this is actually a characteristic of any heated body. So, you know, you don't really see many of these anymore, but when I was a kid, all the light bulbs were basically just these pieces of metal that you drive a current through until they glow red hot, right? Maybe you've seen it, like lava glows red hot, right?
Metal.
Metal, any heated metal, an anvil, if you guys have ever been around like a blacksmith or anything like that. And what's interesting is that the color it glows reflects, first of all, the spectrum given off by any heated body looks exactly like this. It's called a black body spectrum. And the peak temperature, the wavelengths that are at that peak, where the most energy intensity of light is given off, they directly correspond to the temperature of that body, which is really cool because when you look at a star, you should be able to say what temperature it is just by seeing what its peak spectral moment is. Yeah, intensity.
If you've ever used a gas oven, um,
All the time.
and you see that, the flame is blue, and if you drop water on that fire, it turns yellow or, orange. And that's because it's getting cold. Water's
That makes sense.
it's cooling down the flame. It quickly dissipates, but the hotter a flame gets, the colder it gets along with,
That's interesting. Okay, so flames, I'm glad you brought that up. Because flames are weird. So heated bodies do this. Gases are a little bit different. They're kind of weird, actually. So gases, when you heat up a gas, let's say when you combust a gas, or even when you burn a gas, or actually even when you just shine a light through a gas, it does absorb light and it emits light in proportion, but it doesn't give off all of the frequencies. So gases, here's a good comparison. This is a gas lamp down here, and on top is just a regular light bulb, like an old-fashioned light bulb, like when I was a kid. It's just a heated filaments, right? Sort of like the surface of the sun. You put a prism up, and with the heated body, or liquids, heated liquids do this too, like lava or something, you get a whole rainbow, just like the surface of our sun. But with gases, you actually get individual lines that emerge from them. So gases, excited gases, they only give you individual lines. So they only do single frequencies, which is quite interesting. Now this should concern you if anyone's ever told you that the sun is a ball of gas, because
Yeah, I knew you.
the sun is clearly not a ball of gas. And that's going to be revolutionary, and we'll spend most of next semester talking about it. But what is interesting is that the light from a distant star does have to travel through a lot of gas. And we can learn a lot about that gas because as the gas absorbs some of that light, it takes out those colors, right? So we can learn from the fingerprints of, say, the gases and the dust and the particulate matter. I'm just going to stick with gases, but we can learn a lot about what sorts of gaseous stuff is in between stars by the overlaid fingerprints on that nice, clean, continuous spectrum. And the sun, of course, itself, this is a picture of the sun spectrum. The sun spectrum also has little blanks in it, too. These are called the Fraunhofer lines. Why do you think the sun has little pieces missing from it? Hold on one sec. I know you know the answer. Anybody else?
I don't. I'm just guessing.
Yeah. Why has the sun got some gas lines laid over top of it? Yeah.
At the very least from our atmosphere, or just stuff between us and the sun.
You're on the right track for sure. Let's assume this picture was taken from space, though. Yeah.
Is just things. Well, like things
Yeah, there are. Where is that stuff? Yeah.
in space and
Yeah, where though?
matter,
No.
you know?
Anybody? Yeah.
Doesn't the sun have an atmosphere?
The sun has an atmosphere. It's huge. Have you guys ever seen a solar eclipse before? It's pretty crazy. You can actually see the atmosphere spraying out in all directions. It's totally nuts. It's called the corona. It actually has several layers to it, so you can trace it down. The surface of the sun is called the photosphere, and it's that really molten-y looking surface which gives us the continuous spectrum and acts and behaves very much like a molten liquid, although It's apparently an optical illusion. But the sun has an atmosphere, so it has little lines overlaid on it. It makes a lot of sense. So from these little lines, we can actually learn about what's happening in the atmosphere of stars. From the temperature of the profile of the rainbow, the peak of that rainbow, we can learn about the temperature of it. So we get tons of information from spectroscopy. This was an unbelievable revolution in astronomy. All of a sudden we went from just being like, well, there's a big star, there's a little star, to, whoa, these things can actually be accounted for in terms of what they're made out of and how big they are, because temperature actually tells us a lot about the size of stars too. Yeah.
Is does that mean that the peak of the visible spectrum of the sun is yellow?
Let's go back and look at it. Yeah, basically yellow-green. I think that they all combine in such a way that white is what emerges, and that's kind of what we see. But yeah, it is technically it's a yellow star. I think that's a reasonable way of putting it.
Okay.
Yep. So
Would all stars look white to the naked eye if we were in space?
no, some of them have peak temperatures in the blue. They're really hot. Some of the big ones burn really hot. At least they're thought to be big. Um, there may be more to it than that. So this requires a huge conversation because there's serious problems. Oh gosh, I don't know if we have time for this. There's serious problems with treating stars like they're not made out of some sort of molten liquid. Because if you treat them like they're balls of gas, you don't have to consider their material properties at all. So let me make an example to make this real for you very quickly. So if I had a ball of carbon, I could have two balls of carbon. One is just a ball of soot, and one is a diamond that's as big as my hand, right? Very, very different objects. You would probably much prefer me to give you one versus the other, right? But they're both made out of carbon. They're pure carbon. What's the difference between the two?
How much carbon?
Nope, same amount of carbon.
That's
The structure.
The structure, the crystal structure. So the soot is actually arranged in a structure much like I've drawn here, which is kind of a hexagonal lattice that's laid in sheets over one another. The diamond has this kind of cubic crystal structure to it. So just by changing the bonding arrangements of these carbons, literally just by stacking them differently, you get a transparent object in one sense, and in the other one you get a completely opaque object that will give you basically the same properties if heated as the sun itself. Two totally different arrangements, exactly the same composition. Now, this makes a lot of sense because we think about balls of carbon and diamonds as actual materials that have lattices that need to be considered. If we treat the stars like they're just some sort of balls of gas or something, they don't have any of those lattice components that we need to worry about, which means that anything we see, we have to chalk up to size or quantity because we don't have the ability to examine their optical properties based on their actual arrangement of the molecules inside of them, which I think is going to be a massive revolution very soon. But we'll deal with that all next semester. So, questions, thoughts, concerns? Yeah.
we get yet, and I have not yet watched the lecture from last week.
Yeah, it's all good.
But have we gotten yet to the emission of a photon?
The photon. Oh,
Just gonna-
okay. We got 10 minutes. Let's do the photon. Okay, this is great because this kind of brings us full circle because, you know, gases versus bodies, right? So this is really quite interesting. So when they first started when this was actually almost all this work that led to this idea was done by this one gentleman named Kirchhoff. And Kirchhoff started measuring the spectra of heated bodies in a laboratory. And almost as soon as they started doing this, other people came along and they fitted some mathematician buddies of his, this guy named Wien, gave this nice mathematical relationship where he was able to relate the temperature to the shift of that peak, essentially. But one of the consequences that came out of this was that they didn't know that this slope went down on the backside. All of their models just fitted if you can imagine the ramp at the beginning going off to infinity, they basically had the ramp going off to infinity. Now, the result of that was the prediction should be that the blue colors, the X-rays, the ultraviolet stuff, would essentially have infinite power, right? And it fit the data really nicely because all they could observe was the visible stuff anyways. So they had no idea, but they also realized very quickly after they started doing this stuff that like, that doesn't really make sense. Like, how can we have infinite amount of light being generated? Like, wouldn't we just be cooking ourselves with X-rays and ultraviolet rays and all this stuff? This was called the ultraviolet catastrophe at the time, and people didn't know what to do about it. So along comes this dude named Max Planck, a very famous physicist for many different reasons. But Planck realized that he could solve the ultraviolet catastrophe by taking these relationships, and all he had to do was, instead of assuming that light was continuously emitted, that the energy was continuous, that if it was emitted in little chunks, individual actions, he called it the quantum of action, which later took the h bar, which is the Planck's constant, and he inserted that, he could scale the energy of a wave, and the energy of this entire spectrum would fit the curve perfectly. So he basically just tweaked the mathematics by adding a single parameter in that made it so that light had to always happen in whole waves, basically. Individual, he called it the quantum of action, individual actions, right? Now, Planck's quantum of action evolved over the years. Einstein actually contributed to the construction of the photon because Einstein realized that something interesting also happened on the electric side of things. You know, with respect to our antenna that we've been talking about at the beginning of class today, that antennas also absorbed light only in whole wavelengths, and that individual electrons, so individual whole quantized units of electricity, which were starting to be called electrons, could be observed. The amount of excitation of those atomic shells, the way that I'm looking at it, only happen in steps, right? And so Einstein started taking to the idea that there was individual units. He basically revived the particle nature of light as a result of it. Well, it makes sense. There's individual units of light, individual units of electricity. You basically have all of these little particles. It solves your quantization issue, why all of these energetics only occur in discrete steps. Of course, it makes no sense materially, but if you start thinking about the output of these experiments, the measurements themselves, well, in order for the atoms at the other end to actually be driven into a new state of excitation, first of all, those states, those harmonic states, are discrete, just like in the Chladni plate. When you turn the frequency up on the Chladni plate, you don't get structures in between each one of the patterns, right? You get chaos in between because there's just discordant resonance between all of the particles of the system. They're just sort of mashing together. They don't form any balance points. So the same thing is kind of happening at the atom as well. It's being driven into discrete units of excitation. And when it emits light, and when it actually, the only way we would have of knowing that light had even happened was that it did that to another atom at the end, at another antenna, or an individual atom that's acting like an antenna. It has to have a full change, right? And the result of that, of course, is that we are stuck with the photon as the unit, the frequency that's capable of exciting that particular antenna into that action. So the photon is interesting, and it plays in some sense into this picture here, because why is it that a gas would have only one vibratory mode versus a heated body or something that has all of these vibratory modes to it?
Because gas has less atoms.
Yeah, they're individual atoms, actually. So one atom versus a huge array of atoms. What's the difference?
Well, because gases are just a collection of singular atoms,
Yeah,
with no particular structure.
yeah. Yeah, so a little sphere can actually only vibrate in a few different ways. We looked at them when we were talking about these electron orbitals, right? They can really, like, you can vibrate a sphere in a number of ways. You can excite it more and it'll vibrate. And that's essentially what's going on with the gases. You can drive them into different modes of vibrations. Remember, the electricity is always the output of this, whether it's a CCD camera or it's a chemical reaction at the back of your film or whatever. It's always an electric reaction that's the readout of light having happened. Even your eyeballs that are seeing all this light right now are having electrical interactions with this impulse. It's all electricity at the end of the day. So those atoms in the gas, they can only vibrate in a few electrical ways. That makes perfect sense because their antenna shape is essentially limited to a single sphere. With the heated bodies though, like the lava or the anvil or whatever, think about how many unending possibilities you have for antenna shapes. You can have, 3 atoms working together. You could have whole groups of atoms working together. And surely there's some sort of peak antenna overall that seems to be the easiest to vibrate, and that's kind of where your peak temperature is, right? There's some arrangements of the electricity, the antenna action that we talked about at the beginning of class, in these heated bodies, right? But all of those multiplicities of interactions are not available in the gases. They're just discrete individual little units. Yeah.
Wondering if gas emissions would still follow the same trends while only having those
Yep.
wavelengths, like their intensity still changes with temperature the same way.
Yeah, this is just essentially, you drive a current through this little container of gas. You can excite it with like a Tesla coil, or you can just literally put a cathode and an anode on one side or the other. And that's what you see. Yeah. You could heat it up too. I suppose you could combust it as well. But yeah, this is the most you're going to be able to excite these. Now, weird things do happen. So you can actually, if you apply really intense magnetic fields to gases, you can split those lines a little bit. You can get some additional lines that appear. I'm not going to go into like why that is, but you could also pressurize it really hard, and you could start to get a few other frequencies that are spreading out. It might jitter a bit, and you might measure a little bit broader of a peak, but you're never going to get a rainbow out of it. And so,
Which
so you might ask, this is as far as I really want to go with the sun, but it's actually quite hilarious how. So everybody knows this. Everybody knows that gases can't produce rainbows. And so how in the world do astronomers sleep at night with a gaseous sun that produces a rainbow? Well, they have this incredible story about how the photons start off at the center of the sun, and they bounce around inside of this gas for millions of years, and they come out at exactly the right frequency spectrum to look like they're a black body, but they're not really a black body. They just happen to look exactly like one at the end of the day. So it's a very, very like dodgy, convoluted story to actually end up with the picture that we have. But
also, I remember I recently watched a video about the like photon chaotically traveling through the interior of the sun, which fundamentally to me doesn't make as much sense, just for the simple fact that that completely nullifies the wave nature of light.
it makes no sense on
Which
so many different levels.
No,
Uh,
if it's just a particle, there's no way that it could have that wave function. And when you look at quantum mechanics and particle wave duality and whatnot, yeah, they don't they have more wave function than they do particle function.
It is such a heretical argument that I take an entire semester next year to. I'm going to go through every claim made about this and why it makes no sense, and it's quite interesting. But this is a fingerprint, guys. This spectrum, this nice, beautiful curve. It's not a Gaussian. It's not anything else. It's a black body spectrum. The only time we ever see it on Earth in a laboratory is by heating a solid or liquid. We also see it from every single star's surface. So I don't know what in the world we're doing pretending
So
that
we
they're
have a
gases.
solid that's emitting light, right? We've gas outside of it.
Yeah.
We get those lines
Yeah.
like we did before.
Yeah, as gases do. Yeah.
Which means that the sun must
So
be solid with the gaseous.
the reason that this hasn't happened yet is not because it's not a good idea. The reason it hasn't happened is because solids and liquids don't collapse. I'll leave you with that for today.